In the last class, we observed that f of A union B is equal to f of A union f of B for every A subset of X, B subset of X, and f a function from X to A. This result can be generalized for an arbitrary collection of subsets of A. So let's take suppose AI, an element of I, be an arbitrary collection of subsets of X. Still we will get that f of union AI is equal to union of f of AI. This arbitrary, the indexed family of sets, I think that was discussed in the last class. So if you take any, this means this collection can be empty collection, this collection can be finite collection, this collection can be countable or uncountable, whatever be the type of the collection. So this result is true. Proof is very similar to the proof of this fact. So I am not giving the proof. If there is can prove that something belongs to the left hand side if and only if it belongs to the right hand side. But as you observed, a similar result is not true for intersection. There is f of A intersection B need not be equal to f of A intersection f of B. These two things may not be equal in general. But the inverse image, that behaves nicely. That is for suppose f is a function from X to Y and AI, I element of I be an arbitrary collection of subsets of X, so subsets of Y, then F inverse of union AI, I element of I, is equal to union I element of I of F inverse of AI How will you prove this? This can be proved as follows. Suppose X is an element of X. X belongs to F inverse of union AI. This happens if and only if X belongs to the preimage of this set, means the image of this element belongs to the union. That is f of X belongs to the union A. And that happens if and only if an element belongs to a union, if and only if it belongs to one of them. That is if and only if f of X belongs to AI for some I, and that happens if and only if f of X belongs to AI. That happens if and only if X belongs to F inverse of AI for some I. And this happens if and only if X belongs to union F inverse of AI for some I. So that means X belongs to the left hand side if and only if it belongs to the right hand side. Therefore, these two sets are one and the same, equal. So we prove this. And a similar result for the intersection is also true. That is, if AI, I element of I, is an arbitrary collection of subsets of Y, then F inverse of F inverse of intersection AI is equal to intersection of F inverse of AI. And if A is a subset of Y, we can also get that F inverse of A complement is equal to the complement of F inverse of A. That is, inverse image of a complement is the complement of the inverse image. Proof is not difficult. And we can also get that if A is a subset of Y, B is a subset of Y, then F inverse of A minus B is equal to F inverse of A minus F inverse of B. This can be actually derived from that with the observation that A minus B is equal to A intersection B complement. Complement means complement with respect to Y. So using this, you can derive this from that, or you can straight away prove that. So the moral of the story is that inverse image preserves all these operations. That is, union operation, intersection operation, complementation, difference, everything. Consequently, that will also preserve symmetry difference. Pre-inverse image of a symmetry difference is the symmetry difference of the inverse images. So inverse image, that operation preserves all these operations. Whereas the image, that is, image of a union is the union of the images, but image of an intersection need not be the intersection of the images. So you'll have to be careful about it. Another interesting thing is this, suppose B is a subset, F is a function from X to Y, and suppose B is a subset of Y, then you can take F inverse of B. B is a subset of Y, therefore we can take F inverse of B, and F inverse of B will be a subset of X. Then we can take the image of that under F. That will be a subset of Y again, and we can see that this will be a subset of B. But these two sets need not be equal. You can take a function which is not onto. Then you can easily find examples of subsets B of Y for which these two sets are not equal. Of course, this is a subset of this, but these two sets need not be one and the same. And we can see that we can see that F is on to if and only if this happens for every subset B of y. That is, sorry. If and only if these two things are equal for every subset, the set inclusion will always be there, but these two sets are equal for every subset B of y, if and only if F is on to. Now, instead of starting with a subset B of y, we can as well start with a subset A of x. Then f of A will be a subset of y. A is a subset of x, therefore f of A will be a subset of y. Now, for that subset we can take the preimage. That is, you can take f inverse of f of A. You can see that A will always be a subset of this set. But these two sets need not be equal. And we have a result. F is an injection, that is 1 1. F is an injection if and only if A is f inverse of f of A is equal to A for every subset A of x. I am leaving these things as exercises for you. You cannot study mathematics by watching others do mathematics. You can study mathematics only by doing it yourself. So try to do these kinds of exercises. And a lot of exercises are available in books mentioned earlier, especially in the Sham outline series of set theory and related topics. In order to study modern mathematics, I think you should have a good familiarity with the set theoretic operations and things. In the previous class, we discussed equivalence relations. An equivalence relation on a set is a reflexive, transitive, symmetric relation. Now, if x is any set and tilde is any equivalence relation on that, then we can take the equivalence classes of each of the elements. And these equivalence classes form a partition. Suppose P is a partition of x. What is a partition of a set? A partition of a set is a collection of subsets of that set with the two properties. First property is that union of all these subsets is equal to x. Secondly, if you take any two of them, their intersection is empty. That is, any two of them are mutually disjoint. Conversely, suppose you are given a partition P on a set x, we can define an equivalence relation also as follows. That is, we can define for A, B elements of x, we can define A related to B if there exists a P element of script B such that A is an element of P and B is an element of P. That is, two elements are related if there is one set in script P containing both. This relation is reflexive, transitive and symmetric. Therefore, this is an equivalence relation. So, given any equivalence relation, we can get a partition, and given any partition, we can get a equivalence relation. Now, using this, we can even find a 1-1 correspondence between the set of all equivalence classes of suppose script V denotes the set of all equivalence relations on x, and suppose some P denotes the collection of all partitions of x. Then we can find a 1-1 correspondence between these two collections as follows. And these two are the function and its inverses. Kindly verify these things. In order to prove this thing, we'll have to see that if you start with an equivalence relation, then you take the corresponding partition, and from that partition take back again construct an equivalence relation, then you will get the original equivalence relation. And if you start with a partition, then you can get an equivalence relation, and the partition operated from that equivalence relation corresponds to the original partition. If you can prove both these things, that is actually we are proving that there are two functions f and g, so that f combination g and g combination f are identity maps, and therefore they will be inverses of each other, and this will be a 1-1 correspondence. So kindly verify this result. And if you have any difficulty, these results will be proved in the textbooks mentioned earlier. Now, let me give another example of an equivalence relation. That is, suppose f is a function from a set x to y. And if for elements xy of x, I define a relation x related to y if f of x is equal to f of y. This will be an equivalence relation. This tilde is an equivalence relation, because f of x is equal to f of x, therefore reflexive. F of x is equal to f of y implies f of y is equal to f of x, so symmetric. Similarly, you can prove that it is also transitive. So this is an equivalence relation. And once you have such an equivalence relation, that will give you a partition. They will give you a partition of x, and usually that partition is denoted by x over tilde. Now we can even define a function from this partition to y as follows. Let me call that function, say, f tilde, as follows. Because here an element will be an equivalence class. An element here will be an equivalence class. And I want to define the image of that equivalence class. Say I define f tilde of x will be equal to f of x for every equivalence class. This is also a well-defined function. Kindly verify that this is a well-defined function. And also you can see that this function will be 1-1. This function will be 1-1. Of course, there are various other exercises I can suggest, but I am not giving all of them now. But I may give some of these exercises in my website later, so that you can work. You can also get exercises from the books mentioned earlier, as I mentioned. Now we can proceed to the next topic, namely ordered sets. As I told earlier, the modern mathematics is actually the study of abstract structures, and of course suitable functions between them. And what is an abstract structure or an abstract space? You take a set X. A set is just a collection of objects. There is no order. There is no relation between the elements of that set. There is no structure in it. But most of the time we will be interested in sets with some structure. And a set with some structure is called a space, or abstract space. And what is meant by a structure? Vaguely we can say that a structure on a set is some information about the set, about the elements of the set, about the elements of about the subsets of the set, about the subsets of the power set of the set, etc. Some information. We are not specifying what information it is. The information can be of various types. So, if you are just having a set, we know what are the elements of that set, and we know what are not the elements of that set. That is only that. But most of the time we will be interested in some relations between the elements of the set. Sometimes can happen that there is a distinguished element in that set. There is a structure. So, suppose you take a class. A class is a set of students. There is no structure in that. Now I impose a structure. There is a leader in that class. Every class there is a leader. That means there is one element, one distinguished element in that set. That means there is a structure in it. A class with a leader is a structured set. There is a space. Sometimes there will be some order structure between them. That is, the members of a class are arranged in a particular order with serial number. Self itself cannot be, because a set is just in a set there is no additional information. ഒരു സെറ്റിൽ കുറേ എലിമെൻറ്റുകൾ ഉണ്ടാവും. അതിൽ ഏതാണ് ആ സെറ്റിലെ എലിമെൻറ്റ് നമുക്ക് മാത്രമല്ല നമുക്ക് അറിയാൻ പറ്റും. നമുക്ക് ആകെ അറിയാവുന്ന ഇൻഫർമേഷൻ എന്താണ്? Given an object, we know whether that object is in the set or not. That's all. But we don't know any relation between the elements of the set. ഇപ്പോൾ രണ്ട് എലിമെൻ്റ് എടുത്തു കഴിഞ്ഞാൽ അത് തമ്മിൽ എന്തെങ്കിലും ബന്ധമുണ്ടോ നമുക്കറിയില്ല. ഏത് ഓർഡറാണെന്ന് അറിയില്ല. യാതൊരു വിവരമില്ല. അപ്പം ഒരു സെറ്റിലെ എലിമെൻറ്റുകളെ പറ്റി നമുക്ക് യാതൊരു ഇൻഫർമേഷനും ഇല്ല. അതിൻ്റെ സബ്സെറ്റുകളെ പറ്റി പ്രത്യേകിച്ച് നമുക്കൊന്നും അറിയില്ല. എല്ലാ സബ്സെറ്റുകളും നമ്മൾ കണക്ക് തന്നെ, ഒരേപോലെ തന്നെ. അപ്പോൾ അങ്ങനെ എന്തെങ്കിലും ഒരു വിവരം നമുക്ക് അഡീഷണൽ ആയിട്ട് അറിയെങ്കിൽ അതിനെയാണ് സ്ട്രക്ചർ എന്ന് പറയുന്നത്. അപ്പോൾ സെറ്റിലൊന്നും ഇല്ലാന്ന് വരില്ല. സെറ്റ് ഒരു സ്ട്രക്ചറില്ല. സോ സെറ്റിന് നമുക്കൊരു ജസ്റ്റ് സെറ്റിലാണ് നമ്മൾ സ്ട്രക്ചറുകൾ കൊടുക്കുന്നത്, അത്രയും. അപ്പോൾ സെറ്റിന് സ്ട്രക്ചറായിട്ട് വിചാരിക്കേണ്ട ആവശ്യം. അപ്പോൾ ആ സെറ്റിൽ നമ്മൾ അഡീഷണൽ ആയിട്ട് എന്തെങ്കിലും ഒന്ന് ഒരു ഇൻഫർമേഷൻ കൊടുക്കുകയാണെങ്കിൽ ഓർഡർ ഫസ്റ്റ് എലിമെൻറ്റ്, സെക്കൻഡ് എലിമെൻറ്റ്. ഒരു ക്ലാസ്സാണെന്ന് ഇരിക്കുക. അപ്പോൾ ഒരു ക്ലാസ്സിൽ നമ്മൾ സാധാരണ എന്ത് ചെയ്യും? ആ ക്ലാസ്സിലെ കുട്ടികൾക്ക് എല്ലാവരും ഒരു സീരിയൽ നമ്പർ കൊടുക്കും, അല്ലേ? അപ്പോൾ എന്ത് ചെയ്യുന്നുണ്ട്? ആ ക്ലാസ്സിലെ കുട്ടികളെ ഒരു ഓർഡറിലാക്കുന്നുണ്ട്. അറ്റൻഡൻസ് രജിസ്റ്ററിൽ എഴുതാൻ വേണ്ടിയിട്ട് നമ്മളവരെ ഒരു പ്രത്യേക ക്രമം, ആൽഫബറ്റിക്കൽ ഓർഡറിൽ അവർ എഴുതുന്നുണ്ട്. അപ്പോൾ അതൊരു സ്ട്രക്ചർ, ഓർഡർ സ്ട്രക്ചർ. ദാറ്റ് ഈസ് വൺ ഓഫ് ദ സ്ട്രക്ചേഴ്സ്. ഈ സ്ട്രക്ചർ പല രീതിയിലാവാം. ഇപ്പോൾ ഇതുപോലത്തെ ഒരു ഓർഡർ റിലേഷൻ ആവും, വേറെ രീതിയിലാവാം. ഇപ്പം വേറെ രീതിയിൽ എങ്ങനെയാവാം? ഒരു സെറ്റിൻ്റെ ചില സബ്സെറ്റുകളൊക്കെ ഡിസ്റ്റിങ്വിഷ്ഡ് സബ്സെറ്റ്സ് ആണ്. അത് പറഞ്ഞാൽ അതൊരു സ്ട്രക്ചറാണ്. ഇപ്പോൾ ടോപ്പോളജി എന്ന് പറഞ്ഞ സ്ട്രക്ചറാണ്. സപ്പോസ് എക്സ് ഈസ് എ സെറ്റ്. സപ്പോസ് വി സ്പെസിഫൈ ദാറ്റ് സം സബ്സെറ്റ്സ് ആർ called open subsets, some are not, subject to certain conditions. Such a structure is called a topological structure. Or given a set, we can specify the distance between any two elements in that set, of course subject to certain conditions. Such a thing is called a metric, and a set with such a structure is called a metric space. There is another kind of topological structure. Or sometimes there can be operations. For example, suppose you take a set of numbers. You can add two numbers. So that is a binary operation on that. So that is a structure. Sometimes it can happen that on the same set there can be two binary operations, namely an addition and a multiplication, of course, satisfying certain conditions. It's the case with a ring. A ring is such a structure. So there is a structure. Such structures are called algebraic structures. So there are, in general, there are three types of structures, namely ordered structures and logical structures and algebraic structures. Algebraic structures. These are the main three types of structures. And sometimes it can happen that on the same set we can have several types of structures together. On the same, for example, real line is a complete ordered field. And what is a field? Field is a kind of ring. That means there you can add as well as multiply. And it is an ordered field means you can also compare the elements. Any two elements can be compared. There is a order structure there. So an ordered field is a structure. Is a structure with algebraic structure as well as an order structure. Topological group is a structure, is a space with two types of structures, namely a topology as well as a algebraic structure, that is group. So there are several such structures, and sometimes the same set may be endowed with different structures. And of course, these structures need not be of the same type. One can be ordered structure, the other can be topological structure, and the third can be algebraic structure. But of course, when you put more than one structures in the same set, we will ensure that they are compatible in some sense. Otherwise, that will not be very meaningful. But the point is that generally we can classify these structures into three types: ordered structure, topological structure, and algebraic structure. And here we are concerned only with the order structures. So what is meant by an order structure? That is, we say that some elements of that set can be compared. There is some order of precedence. For example, you take set A, you take the power set of that, and in that power set we can consider the set inclusion. So given any two subsets, say B1 and B2, B1 is a subset of A and B2 is a subset of A, we can ask whether B1 is a subset of B2 or not. Or to take another example, you can take a collection of numbers, say the set of all real numbers. We can ask whether two numbers, given two numbers x and y, we can ask whether x is less than or equal to y or not. So these are examples of ordered sets. So first let me define a partial order. A partial order
the order set surveying property.
That is what I am defining. There are not only, in fact, there are several types of order structures. One type is called partial order. So, let me define it. A partial order on a set is a relation less than or equal to. A partial order on a set X is a relation less than or equal to on X, such that which is reflexive, antisymmetric, and transitive. A reflexive, antisymmetric, and transitive relation is called a partial order. Now, what is meant by these properties? Reflexivity. That is, less than or equal to reflexive means x is less than or equal to x for every x element of x. And antisymmetric means for every xy in x, x less than or equal to y and y less than or equal to x implies that x is equal to y. This property is called the antisymmetry. This property is called reflexivity. This is called antisymmetry. In other words, antisymmetry says that if x is different from y, then either x is not equal to y, not less than or equal to y, or y is not less than or equal to x. So antisymmetry means that if x and y are two elements of the set, then x not equal to y implies that either x is not less than or equal to y, or y is not less than or equal to x. Or to state it in another way, we can state that for every x and y, x less than or equal to y and y less than or equal to x means, implies that x is equal to y. These two things are one and the same. One is the contrapositive of the other implication. And what is meant by transitivity? For every x, y, z in x, x less than or equal to y and y less than or equal to x, z implies that x is less than or equal to z. This is the transitive property. So a partial order is a relation with these three properties: reflexivity, antisymmetry, and transitivity. In fact, there is a weaker property called pre-order, a relation less than or equal to on a set x is a pre-order if it is reflexive and transitive. This is a more general concept, because clearly every partial order is a pre-order. Every partial order is a pre-order. But the converse is not true. Let me give one example. You take the set of all integers. Now consider this relation, divides. This relation is reflexive, that every integer divides itself. For every integer x, x divides x. And this relation is also transitive. X divides y, y divides z implies x divides z. So this relation is reflexive and transitive. Therefore, this is a pre-order. Whereas this relation is not antisymmetric, in the sense that 1 divides minus 1, and minus 1 divides 1, but 1 is not equal to minus 1. So in the set of all integers, divides is not a partial order, but it is a pre-order. Whereas, suppose you take the set of all positive integers and take again the same relation, divides. Here this relation is reflexive, transitive, and also antisymmetric. Because if you take any two positive integers a and b, a divides b and b divides a implies a is equal to b among positive integers. But among integers, the result is not true, because if you take any integer a divides minus a and minus a divides a, but a need not be equal to b unless a is equal to 0. So this divides is a partial order on Z plus. Whereas divides is a pre-order on the set of all integers. Another example is this. If you take any set A, you take power set of A, then subset of is a partial order. Why? Every set is a subset of itself. So that is reflexive. It's transitive. If A is a subset of B and if B1 is a subset of B2 and B2 is a subset of B3, then B1 is a subset of B3. So that is transitive. And if A is a subset of B1 is a subset of B2 and B2 is a subset of B1, then B1 is equal to B2. So that is antisymmetric also. So in any power set, in the power set of any set, this relation is a partial order. And if less than or equal to is a partial order on X, on a set X, the ordered pair X less than or equal to is called a partially ordered set. And sometimes that is abbreviated as poset. So the definition is that a partially ordered set is an ordered pair X less than or equal to, where X is a set and less than or equal to is a partial order on it. Similarly, a preordered set is an ordered pair. If you is a if less than or equal to is a preorder on a set X, then this is called a preordered set. Poset means a partially ordered set. Some people define a partially ordered set as a set with a partial order on it. So in some old books, I think you can see such definitions. Or it's a set on which there is defined a, or something like that. Our style is to define all these things as sets. An ordered pair is a set. So there is no harm in defining a set as a partial ordered set as an ordered pair. Because an ordered pair is a set. And our idea is to define everything in mathematics as sets. So, and I think that is a modern trend. In most of the books you can define all these abstract spaces as ordered pairs or ordered quintuples, quadruples, etc.